Hi everyone. Today I'm going to talk about the characteristics of acids and bases. So this is the first lecture in our very last unit, acids and bases. So first and foremost, we're just going to go over some general characteristics of acids and bases. So the first one is that acids are going to turn litmus paper red and bases will turn litmus paper blue. Now, if you've never heard of litmus paper, basically what this is little tiny strips of paper, and you can put it in your solution to see whether it's acidic or basic. Now, it's kind of confusing because there's different types of litmus paper. You can see that here an acidic solution will turn blue litmus paper red, and then a basic solution will turn red litmus paper blue. So we have blue litmus paper and red litmus paper, but you just have to remember that acids are going to be red, bases are going to be blue. That's all you have to remember. And it's easy to remember because B, base, starts with B, and so does blue. Now, there's also something called a universal pH paper, and it comes with a little key like this you can see on the screen. And basically, if you have an acid, then it's going to be in the red realm down here. And then if you have a base, it's going to be in the blue realm. So it has to do with the actual pH of the solution, which I'll talk about in a second. But that's what litmus paper and universal pH paper is. The next thing is that they are both conductive, and we know that in order to conduct electricity, we have flowing charges. So we need a charged solution. So because of that, when acids and bases go into solution, they do dissociate, and we'll talk about reactions and things like that. But because we have those positives and negatives, they're both very conductive. Acids react with metal to form H2, and then bases turn pink in phenolphthalein. Now, phenolphthalein is something that we use in something called titration. And we'll talk about titration later this unit. Basically, what happens in titration is that we have an acidic solution, and then we are trying to find out how much base we need to neutralize it. So we're dripping base into the acidic solution. Now, in this acidic solution, you also have that phenolphthalein. So it's an indicator. That's what we call it. And so every time you drip some base in there, it turns pink a little bit. And then you usually, when you're in the lab, you usually have a little stirring rod thing in there, and the pink just disappears because the base is dispersed in solution, but the solution is still overall acidic. It's kind of cool. It looks like a magic trick, kind of. And then when it's neutralized, you'll get like a light pink color. So the pink doesn't go away like it did before. And then if you overshoot it, meaning you added too much base, then it's going to be a deeper pink. So it's pink, again, because this phenolphthalein turns pink when it is in a basic solution. Acids have a sour taste and bases have a bitter taste. And this makes sense, right? Because if you think about something like a lemon, has citric acid in it and it's sour. Now, bases, you might not know off the top of your head what a base is, but if you've ever accidentally put too much baking soda in your cookies or something like that when you make cookies, they make your cookies bitter because baking soda is a base. Something else that's basic is soap. If you've ever tasted soap, I hope not because it's kind of gross, but if you have ever tasted soap, it's also bitter. It tastes really bad because soap is basic. Acids have a low pH. So our pH scale, we'll talk more about this later this unit, but it's from 1 to 14. 7 is our neutral pH, and so anything below 7 is going to be an acidic pH, and then everything above 7 will be a basic pH. Acids neutralize bases, bases neutralize acids, and we'll talk about neutralization reactions in a minute. And then acids are going to sting when it gets on your skin. If you have a really high concentration of acid, it will burn your skin, basically. And if you have a cut on your hand and accidentally get lemon juice in it, it stings really bad. And it's because it's an acid. And then bases feel slippery. Like I said, soap is a base. So the reason that your hands feel slippery when you're washing your hands, or your body when you're washing your body in the shower or something like that, is because soap is a base. So it feels slippery. Now, there's different types of acids, or classifications, we'll talk about more classifications later, but different types. We have Arrhenius acid, and that is a substance that releases H plus ions into solution. Now we call H plus ions protons. So when you hear me say, oh, it releases protons into solution, that's what I'm talking about. I'm talking about hydrogen plus those ions. So for example, if we looked at a reaction with this, I have a hydrochloric acid and it's going to dissociate in solution to H plus, our protons, and Cl minus, our chloride ion. So there's going to be a bunch of protons in solution because that acid dissociated in solution. There's also a classification of a Bronsted-Lowry acid, and that's a substance that acts as a proton donor. So if we have HCl, my hydrochloric acid, going into water, it can release those H plus ions into solution, and then water can gain that proton. And so what it becomes is H3O plus, which we call the hydronium ion. And then we also get the chloride ion in solution as well. Again, like I said, this is called the hydronium ion. So that's just the name of that. So when you hear me say the hydronium ion, that's what I mean, H3O plus. And so you can see here that hydrochloric acid can be both an Arrhenius acid and a Bronsted-Lowry acid. So you can be both. It doesn't mean like an acid is just one or the other. You can also be both. And then we also have something called a conjugate acid, which is the acid that's formed from receiving a proton. So an example here would be the hydronium ion in the previous example. So we formed this acid, and it was formed because it received that proton from hydrochloric acid. On the other hand, bases, we have an Arrhenius base, which is a substance that releases hydroxide ions in a solution. And we already know what a hydroxide is. You should know what hydroxide is because we learned about it in our polyatomic ions. So for example, if I have sodium hydroxide, that is going to dissociate into sodium, the sodium ion and the hydroxide ion in solution. And then a Bronsted-Lowry base is a substance that accepts protons. So if we looked at the equation for this, we have NH3 plus H2O goes to hydroxide plus NH4 plus. So in this case, it's important to point out that bases don't always have hydroxide in them. A lot of the time, like acids usually start with an H, always start with an H. Bases, a lot of the time students will think, oh, they're only things with an OH at the end. However, it's not always the case. So in this case, NH3 is our base because that is the thing that accepted that proton, right? It accepted the proton to become NH4. So that in this case is our base. And then we also have something called a conjugate base, which is a base that's formed as a result of losing a proton. So in this case, our hydroxide ion is the conjugate base because water lost the proton in order to become the hydroxide ion. So if we're going to do an example here, we have this reaction and we want to identify the acid, base, conjugate acid, and conjugate base. So remember, a base is something that is going to gain a proton. So in this case, my NH3 is going to be my base. An acid is something that's going to lose that proton or donate the proton. So in that case, this right here is my acid. That is acetic acid. And then my conjugate acid is the thing that got the proton. So because this one right here, NH4 plus, my ammonium ion, has received the proton, that's going to be my conjugate acid. And then the conjugate base right here is the thing that donated that proton. So we have our conjugate base there. All right, so neutralization reactions are going to be when an acid and base react with one another. So in this case, the acid is going to lose a proton or donate the proton, and then the base is going to gain the proton or accept the proton. Now, in these neutralization reactions, usually a salt and water is formed in our products. And what I mean by salt, I don't mean just like table salt. Remember, and table salt is NaCl, which is a salt. So a salt is an ionic compound. So anything that has a positive cation and a negative anion, that's what we call a salt. So this is going to form a salt and water. Now, this is a double replacement reaction. So if I have an example here, in this case, I have barium hydroxide reacting with nitric acid. I think that's what that's called. We'll go over acid naming in a couple lectures. But here, that hydroxide is going to be my base because it is going to receive that proton. And then this right here is my acid because it is going to lose the H plus, my proton. It's going to donate its proton. All right, so I have my double replacement reaction and I get barium nitrate and water. So this right here is my salt, barium nitrate. I have my positive cation and my negative polyatomic anion, and then water as my products. Now, like I said before, there are different ways to classify an acid. We only classify acids, really. We don't really classify bases as much. But there's two ways to classify an acid. And the first one is based on the number of acidic hydrogens. So if I have a monoprotic acid, what this means is that the solution only contains one acidic hydrogen. Remember, mono means one. So something like HCl, hydrochloric acid, that's going to be a monoprotic acid because it only has one hydrogen. And the reason it only has one hydrogen is because chlorine is only a -1 charge. So I only need one positive to balance out that -1 charge. I also have something called a diprotic acid, and that is a solution that contains two acidic hydrogens. So something when the anion is a -2 charge, I need two positive ones in order to balance that out. So I have two hydrogens here, H2SO4. And then also we have a polyprotic, which is a solution that contains more than two acidic hydrogens, so 3 and up. So this would be an example here, H3PO4, phosphoric acid. And then the other way to classify an acid is based on the number of elements in the acid. So if we have a binary acid that's only made up of 2 elements, remember bi means 2. And so examples of this would be hydrochloric acid and hydrofluoric acid. We have just HCl and then just HF. And then we also have ternary acids, and this acid is made up of 3 elements. Ternary, TER, that's like a 3, right? That's a prefix for 3, one of them. And here's some examples here. We have acetic acid and sulfuric acid. No, sulfic? I forget what that name is too. Again, we'll go over acid naming in a bit. But in the first example here, I have hydrogen, carbon, and oxygen for my 3 elements. And then in the second example, we have hydrogen, sulfur, and oxygen for the 3 elements. So that's a ternary acid. And then last but not least, I want to talk about anhydrides. Now, anhydrides, the definition here is a substance that forms an acid or base when placed in water. So by itself, this thing is not an acid or base, but it's going to react with water to form an acid or a base. And so there's 2 examples here. Number 1, the first one is metal oxides. And when metal oxides react with water, they're going to produce a metal hydroxide, which is a base. Remember, OH, our hydroxide, that's a base. So an example here would be sodium oxide reacting with water. So all we're going to produce is the metal hydroxide, so we will produce sodium hydroxide. So you have to make sure when you do these reactions, you have to make sure that you're balancing the equation. Sodium hydroxide here, remember we balance both charges and the overall equation. So hydroxide is a -1 charge, sodium is a +1, so I don't need multiple sodiums. And then I'm going to balance the equation. I have 2 sodiums over here, so I need 2 over here. And then now we can see I have 2 oxygens here, 2 oxygens here, 2 hydrogens here, and 2 hydrogens here as well. Another example is magnesium oxide reacting with water. I'm going to produce magnesium hydroxide. And then here we can see that magnesium is a +2 charge, oxygen is a -2 charge, so that is balanced. Notice how sodium we had 2 of them because I need 2 +1s in order to balance out the -1 from oxygen. And then so I'm going to make magnesium hydroxide. Hydroxide is a -1 charge, so I need 2 hydroxides to balance out that magnesium here. So we can see that we have 2 of these -1 charges to balance out the +2. So those are metal oxides. Again, when they react with water, they're going to produce a metal hydroxide, which is a base. Now, on the other hand, we also have something called a nonmetal oxide, which is going to form an acid with water. So, nonmetal meaning these are the things in the periodic table that are on the right-hand side, like the upper right-hand side of the periodic table. Remember, metals are like on the left-hand side. We have our alkali metals, our alkaline earth metals, our transition metals. So, nonmetals are going to be like our covalent compounds. So, we have, carbon dioxide is going to be my first example. And I have another example in a bit. So again, these nonmetal oxides, so something like carbon dioxide, when it reacts with water, it's going to form an acid. So what we get here is H2CO3. Now, the way that we're going to do this is we're going to make a water sandwich. So what you do is you split water down the middle. So you have your H2 and then your O, and then you put your nonmetal oxide in the middle. So, and then you combine what you can, meaning you combine the oxygens usually, like in this example and the next example I have. So for another example here, I have nitrogen dioxide reacting with water. And so again, we want to split water down the middle. So I'm going to have H2 and then my O on the other side. And then I'm going to put my nitrogen dioxide in the middle. And so I should get hydrogen, nitrogen, and then look, I have 3 oxygens right here. So we're combining that. And so I get H2NO3 for my product in that reaction. And that is those 2 anhydrides. So remember, when we have a metal oxide that's going to form a base, when it reacts with water, it forms that metal hydroxide. And then when we have a non-metal oxide, it's going to form an acid with water, and you do your little water sandwich. So that is all I had for you for the introduction to acids and bases. You do have an assignment on Canvas, and I will be honest, the assignment looks a little long, but I promise that it goes very fast. In the very beginning of it, it's just basically, characteristics of acids and bases. So one of them is taste sour. That's going to be an acid. And so all you're doing is saying acid base, whatever. And then you do have some reactions like we've gone over today. So if you have any questions, please feel free to email me, and I will see you all in class.